Hello everyone. Welcome to this introductory video on Python's asynchronous input-output, or Asyncio. In this video, we'll explore the fundamentals of asynchronous programming in Python, focusing on how to use the async input-output framework along with the async and await keywords. We'll cover the basics of coroutines and tasks, and illustrate these concepts with practical examples. By the end, you'll have a solid understanding of how to write efficient, non-blocking code using async input-output. First, it's important to understand the difference between synchronous and asynchronous programming. In synchronous operations, tasks are executed sequentially, meaning each operation blocks or waits until it's fully completed before the next one starts. Asynchronous operations, on the other hand, allow tasks to run concurrently without blocking the main thread. This is achieved by switching between tasks while waiting for input-output operations to complete. Concurrency refers to managing multiple tasks by switching between them. Asynchronous input-output is particularly useful for input-output bound tasks, such as those involving network requests or file operations, where waiting for external resources is common. Let's look at a comparison of the code. Consider synchronous code where a function sync_function calls getData from API, and then getMoreData. Each call waits for the previous one to complete. Now, compare it with the asynchronous code where the function async_function, defined as asyncdef async_function, also calls getData from API, and then getMoreData but uses await. This allows other tasks to run while these functions are waiting for data. Let's dive into coroutines and the async or await syntax. Coroutines are special functions that can pause their execution and yield control to the event loop, allowing other tasks to run. They're defined using the asyncdef syntax and must be awaited or scheduled to run. When a coroutine is called, it returns a coroutine object which can then be used in asynchronous operations. Importantly, coroutines can contain await expressions, which are points where the coroutine can pause execution. Here's some sample code that shows how to define and use coroutines. Firstly, import the Asyncio library. Then define a coroutine named fetch_data with the asyncdef syntax that accepts a URL as input. This function simulates a network delay using asyncio.sleep for 1 second, and then returns a formatted string. Another coroutine named main is defined to use the fetch_data coroutine, awaiting its result and printing it. Finally, the asyncio.run function is used to execute the main coroutine. Now let's explore tasks and concurrency. Tasks are used to schedule coroutines to run concurrently. You can create a task using the asyncio.create_task function. This allows multiple coroutines to run seemingly at the same time, without blocking each other. Tasks can be awaited, cancelled, or grouped together, making them perfect for managing independent operations. Here is the code that shows how to run tasks concurrently. First, import the Asyncio module. Define a coroutine fetch that simulates fetching data from a given URL with a 1-second delay. Then define a main coroutine that creates 2 tasks, Task 1 and Task 2, using Asyncio create_task, each calling the fetch coroutine with different URLs. The results are awaited and returned as a list. Let's look at a practical example: web scraping. Using asynchronous input-output for web scraping has significant advantages. You can fetch multiple pages concurrently, dramatically reducing the total execution time. It allows you to handle network timeouts gracefully, process data as it becomes available, and efficiently scale to hundreds of requests. The code here demonstrates an asynchronous web scraping example using the AIP library, which is an asynchronous HTTP client. First, import the Asyncio and AIP libraries. Define a coroutine called fetch_page that uses an AIP client session to get the text content of a URL. Define another coroutine called scrape_sites that takes a list of URLs, creates tasks for each URL, and gathers the results using asyncio.gather. The example then defines a list of URLs and runs the scrape_sites coroutine to fetch the content of those websites concurrently. Let's discuss some best practices and common pitfalls when working with async input-output. It's crucial not to use blocking calls within coroutines, as this can negate the benefits of asynchronous execution. Always await coroutines to ensure they're properly executed. Use Asyncio.gather for running tasks in parallel, and handle exceptions with try or except blocks to prevent unhandled errors. Setting timeouts for network operations is also important to avoid indefinite waiting. When available, use asynchronous context managers to manage resources properly. Here are the code examples demonstrating handling timeouts and proper exception handling. The first function, fetch with timeout, uses Asyncio to timeout to limit the execution time of the fetch data coroutine. If a timeout error occurs, it catches the exception and returns a message. The second function, safe operation, demonstrates proper exception handling within a coroutine, catching any exceptions that occur during the execution of a risky coroutine and printing an error message. Finally, let's touch on some advanced async input-output features that go beyond the basics. Semaphores can be used for controlling concurrency, limiting the number of coroutines that can run simultaneously. Understanding event loops and custom executors allows for fine-tuning of how asynchronous tasks are scheduled and executed. Async generators enable streaming of data. Additionally, there are synchronization primitives available like locks and events. Queues for producer-consumer patterns allow you to make your program to have first-in, first-out structure. Async input-output also supports subprocesses and shell commands, enabling you to run external processes asynchronously. The code shows how to limit concurrency using a semaphore. The fetch with semaphore coroutine takes a semaphore object and a URL. It acquires the semaphore before fetching the data and releases it afterwards, limiting the number of concurrent fetch operations. The main coroutine creates a semaphore with a limit of 5 concurrent requests, generates a list of URLs, creates tasks for each URL using fetch with semaphore, and gathers the results using Asyncio.gather. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.